Okay, so as you can see, we're building things on top of ideas on top of ideas. And the latest thing that we're going to look at is relations. Now, in terms of what a relation is, you can think about it as a database to some degree. Now, you might disagree with that, but the idea would be that you have, I'll show you the sense in which it's a database. So you're going to have some pieces of data. So for example, let's say age, let's say gender, let's say occupation, something like that. And you're going to have data points. Now maybe there's an ID as well. Okay. So let us explain in what sense a relation. No, I haven't even said what a relation is yet, but I'll show you what I mean. So suppose ages, let's say 18, 17, let's say 19, gender, let's say male, female, occupation, okay, let's say unemployed, shop worker, and let's say for the 19-year-old bar worker. Okay, and the ID will be, well, the ID can be the same as the row number 1, 2, 3. Now what these things are ordered tuples. So we've got say one element of the database would be 18 for age, the first thing, male for gender, the second thing, unemployed for occupation, the third thing, and ID number is 1. And this would be an element of a Cartesian product of the ages. You can use natural numbers for argument's sake. The genders, I'm going to just say there's a number of different genders given as letters in some alphabet G. The occupation, similar story, given as letters in some alphabet O. And the ID number, let's say, is a natural number as well. Now, if you form all the possible ordered tuples from here, like for example, 1 male, unemployed, 72, there mightn't actually be someone in the database with those characteristics. So a database will not contain all possible ordered tuples, just some of them. Now here I've said that a relation isn't ordered. These are obviously not ordered pairs, but you, the same way that we had Cartesian products of more than one set, you can have we're going to study binary relations, but you can extend that to relations on more than one set, but we're not going to actually do that. But it's just a way of thinking, how is this connected with computer science? This is how you could do it. Okay, so getting away from talking about databases, let's be more precise. If A and B are sets, a relation or between A and B is a subset of a Cartesian product B. So it's a subset, which means that, remember what a subset is, you go through this set and you say, look at the elements, is it in it, yes or no? So if you think about the yeses and putting them all together, you get a subset. So a relation, and these are ordered pairs, so you get some ordered pairs. If you want to say that A in A is related to B in B, so this is the kind of language of relation, you can either write that the ordered pair AB is in the relation, or another way is writing A related to B. For example, let P be the people in this room. Well, that's obviously no good. This class. I think I would have, okay. People in this class union the lecturer, which is me, JP. And A being natural numbers, we can define a relation. Now we're not going to take all the ordered pairs, because we're not going to pair me, for example, with 179,000, because I want to just take some of the things. I want the relation to mean something, and I'm going to take the relation of age. So we're going to say a person is related to a number if the person is that age. So let's write that down. So let's say a person is related to an age, or another way, so that's one notation. The other is writing person age is in this relation, this is not set of real numbers, if person P is age A. So for example, I'm JP, I'm related to 35, so I can write it as JP 35 is in or JP is related to 35. You can also represent these graphically using what's called a digraph. So let A be 2, 3, 5 and define a relation or an 8 now. So think now, you can make all the ordered pairs where the first thing is 2, 3, 5 and the second thing is 2, 3 or 5. We can do that. Maybe, okay, so there would be 9 of those. Let's take some of them. So let's say the relation R is, let's say 2 is related to 2. Let's say 2 is related to 3. And let's say 2 is related to 5. Let's say that 3 is related to 5. And 5 is related to 2. And 5 is related to 5. Now notice, unlike when you have a Cartesian product of a set with itself, you can have what looks like repetition. Now it's not really repetition because it's a first 5 and a second 5. It's a little bit different. Okay, so how we the best way to represent a relation, the best way to analyze them, is to draw what's called a digraph. Now this is a relation that is on it. This is called a relation on A. If it's so, you can have a relation between A and B, or you can have a relation on A. And this is typically the one we're going to be looking at. So the elements of A become nodes. So for example, now here there's just 3 nodes, 2, 3, 5. So 2 is a node, 3 is a node, and 5 is a node. And what we do is, if elements are related, we draw an arrow between them. Now there has to be an arrow. An edge isn't good enough because there's an order involved, and it's from the first thing to the second thing. So 2, 2 is an arrow from 2 to 2. We just draw a little loop like that. Okay, so that shows that 2 is related to 2. We also have 2 is related to 3, so we draw an arrow from 2 to 3. We also have 2 is related to 5, like this. 3 is related to 5. 5 is related to 2, so that's a double edge. Okay, there. And finally 5 is related to 5. Now this is obviously connected with networks and stuff like that. So for example, you could have a relation on the set of Twitter accounts, and what would it be? An account A is related to account B if A follows B, for example. Okay, but these digraphs. Oh, I forgot about the arrow diagram. So this is the digraph. Now there's going to be various different pictures we'll use to analyze things. Don't mix them up, and how you don't mix them up is you do lots of questions. So the arrow diagram I forgot about. So the arrow diagram goes like this. You put the first copy here, the second copy here. So these are sets A and B. You put the elements in 2, 3, 5, 2, 3, 5. Sorry, this is not B, this is also A because it's a relation between A and A. Now this is actually not the way to analyze these. There's just better ways. This one is better. You'll see this as we go on. What have we got? 2 is related to 2. 2 is related to 3. 2 is related to 5. 3 is related to 5. 5 is related to 2. And 5 is related to 5. Now, already it's not so good as this. We're going to, the problem is you have, say, if you think of these inputs and outputs, you have one input having 3 corresponding outputs. When every input has a single output, that's what's called a function, and we'll look at that a little bit later on. Relations between ordered sets can also be represented using a coordinate graph. In other words, if you have an order, plot these points. Now, to be very careful, as we'll see, you don't join the dots. Okay, and that will become a bit clearer later on when we talk about functions. Okay, Now I'm going to need some kind of a thing here to do this up. So what we'll do here is, okay, let's just write down the relation. So let's say that, okay, let's say 2 is related to 1. Say 2 is related to 4. No, I'm just making these up. 2 is related to 6. We can have 3 related to nothing, that's fine. 5 related to 3. 5 related to 4. It's a perfectly good relation. And what you can do is plot these points. So this is a subset of Cartesian product of A and B. So it's not all of the elements of A times B. For example, where is, so actually we should write down what A and B are. A is set 2, 3, 5. And B is the set 1, 2, dot, 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 all the way up to 8. Okay, so the Cartesian product would be all the points, showing you that there would be 8 by 3, 24 of them, but a relation is a subset, just some of them. So for example, we'd get 2 is related to 1, so you put in the point 2, 1. 2 is related to 4, so you go 2 along the x, 4 along the y. 2 is also related to 6. 5 is related to 3, and 5 is related to 4. Now again, it's actually not as good as the arrow, not the arrow diagram. So this is a coordinate graph, arrow diagram, digraph, directed graph. This is the best one. Okay. We always put the first set A along the horizontal x-axis and the second along the vertical y-axis. So don't join the dots. Because there's only 1, 2, 3, 4, 5 points in this relation. That's it. Okay. If A and B are equal, then R is a relation on this. We've seen this before. We call a relation between S and S a relation on S. So what have we got? For example, let S be the set ABC. A relation on ABC is any subset of S times S. So I think what we might do here is just write down S times S. Now remember what a subset is. That's a set, and it's a series of answers to the question, is A in there, is B in there, is C in there? Yes, no, yes, no, yes, no. Let's go with no, no, no is the empty set. Yes, no, no is the set containing A. We need these curly brackets. No, yes, no is the set containing B. No, no, yes is the set containing C. Yes, yes, no is the set containing A and B. Yes, no, yes is the set containing A and C. And no, yes, yes is the set containing B and C. I feel like I've already said that, but it's not actually written. And then yes, yes, yes. Now I could write the set containing A, B, and C. I could write that. That's no problem, but it's nicer just to write S. So a relation is a subset of this. So I just have to take some of these. So say for argument's sake, I'm an idiot. I'm an idiot because this is not, oh dear, sorry, my apologies. This is not S times S. This should be Cartesian product. I'm really sorry if I confuse you. So this is the power set. This is not what we want. S times S is all the ordered pairs. So the first thing in ABC, the second in ABC. So for example, AA, sorry about that now, that's embarrassing. AB, AC, okay, BA, BB, BC, and then CA, CB, CC. So this is the full Cartesian product, and I'm saying that a relation is a subset of this. So I wasn't thinking, but it's like is this in your relation? Yes or no? 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 So for example, suppose we answer 3 yeses, a no, a yes. So yes, yes, yes. a no, a yes, and let's say the rest of them are no's. So that would be an example of a relation on S. Relations can be very convenient language in mathematics. How many relations on a set? So this is a good question. So we'll do it just with the example if S was equal to 3. So how many possible subsets of this? So let's see. The question is, what is the size of... So remember, this is all the Cartesian products, and a relation is a subset. So P of S times S is the set of subsets of this. And each thing, so this thing here, set of subsets of S times S, and that's exactly equal to the set of relations, because a relation is a subset of S, Cartesian product S. What we have to do is combine a number of facts we've seen already. So the power set of any set, the number of elements in it, we've seen previously, is 2 to the power of the number of elements in the set. Okay, and we've seen previously that the number of elements in a Cartesian product is the number of elements in the first set times the number of elements in the second set. So the answer to the question in general is how many relations on a set S is 2 to the power of number of elements in S squared. And for example, if we're looking at S equal to 3, it'd be 2 to the power of 3 times 3, which is 2 to the power of 9, which is, I think it's like 500 or something. Let's check it out. Yeah, 512. So there's 500 possible relations here. What that actually means is if you want to take 3 elements and you want to draw some arrows between them, there's actually 512 different ways of doing that. Okay, so let's look at some examples. So let's set M be 1, 2, all the numbers up to 10. Define a relation R on M. So we're going to have relations between numbers between 1 and 10 and numbers between 1 and 10. So they're going to be ordered pairs. Some ordered pairs, a subset of the Cartesian product of M with itself, such that xy is in the relation if and only if there is a number k such that, I need to rewrite this, so y is equal to kx. In other words, x is related to y if y is a multiple of x. Okay. So the question here we have is, what is 1 related to? Okay. So 1 is related to 1 because 1 is a multiple of 1. 1 is related to 2. Say if I take 1, 3 here. Well, it's y is a multiple of x. The second thing is y. Is 3 a multiple of 1? Yes, so it's related. So 1 is also related to 4. Also 1 is related to 5. We 1 related to 6, 1 related to 7. 1 is related to 8 because 8 is a multiple of 1. 1 is related to 9. 1 is related to 10. What about 2? So is 2 related to 1? No, because 1 is not a multiple of 2. Is 2 related to 2? Yes, because 2 is a multiple of 2. 2 is related to 3? No, because 3 is not a multiple of 2, but 2 is related to 4. Ask yourself, is 2 related to 5? Is 5 a multiple of 2? No, so it's not there. But 2 is related to 6. 2 is related not to 7 but to 8. And 2 is related to 10. What's 3 related to? Well, 3 is related to 3 because 3 is a multiple of 3. Is 3 related to 4? No, because 4 is not a multiple of 3. We do have 3 is related to 6 and 3 is related to 9. Remember, a number is related to another one if the second number is a multiple of the first. That's what this relation is. What else we got? 4 and 5. Well, we're just going to have 4 is related to 4. 4 is related to 8. It's getting quite long. 5 is related to 5. And 5 is related to 10 because 10 is a multiple of 5. The others are a bit easier because only 6 is a multiple of 6, only 7 is a multiple of 7, only 8 is a multiple of 8, only 9 is a multiple of 9, because we're only working with numbers between 1 and 10. That's where our relation is. And finally, 10 is related to 10. So there's 27 elements. You definitely couldn't draw an arrow diagram here. It would just be a nightmare. I mean, look at this. It'd be horrible. Might be possible, but actually this is an example where the coordinate graph is perfect. So we have 1 is related to 1. So we have 1 along the x, 1 is related to everything. I'm just going to change here because it's probably a bit confusing with 1x. Should be maybe 1y for all y. Okay. So we have 1 is related to 1, so draw that point. 1 is related to 2. 1 is related to 3. 1 is related to 4, 5, 6, 7, 8, 9, 10. We had 2 is related to 2, 4, 6, 8, 10. 3 is related to 3, 6, 9. 4 is related to 4 and 8. 5 is related to 5 and 10. And then we had 6 is related to 6, 7 is related to 7, 8 to 8, 9 to 9, 10 to 10. So that's what we're, excuse me. That's everything there. Okay. Now the next question, I think with a few more examples, would probably leave to another lecture.